Okay, we're going to go ahead and get started this morning. Um, if any time during our little presentation this morning you have any questions, please feel free to use the chat box. Um, I'll have it open here and try to answer questions as they come in. So we're going to go ahead and get started. Today's webinar is on pump selection. And uh, for those of you who don't know me, my name is Scott Carlson. I've been with the company for almost 25 years now, and we set up these what we're calling VTMs, virtual training modules, um, back in 2020 during COVID as a way to communicate between distributors, and we find it very helpful to be able to get you guys some uh, training as much as possible. So we've been hosting uh, a couple of these every month. So right now we have pump selection. Later this afternoon, we'll have a website tour. So if you haven't registered for that, please do. There's a lot of information on our website that is not uh, really that prominent unless you've been there and have been shown. But we'll go ahead and get into the pump selection here. We're going to talk a little bit about, we're going to start with the simplest way to select pumps, and then we're going to get more and more complicated. It won't be too bad. This should be pretty straightforward if you've been working with pumps for a while. Some of this will probably be review for some of you. So we are going to start here. Oh, okay. Um, so a few quick pumping facts that have nothing to do with regenerative turbine pump selection, but it is entertaining. Largest pump in the world is a Pentair Fairbanks. It's a propeller type pump. Does almost 1 million gallons a minute and requires almost 5,400 horsepower to operate. One of the smallest pumps in the world is created by a bunch of engineers in a school, and it was designed to help disperse medication. It's 1 nanometer in size and spins at 18,000 RPM for over 15 hours. That's kind of cool. The highest pressure rotodynamic pump in the world is a Sulzer pump. It's for seawater injection. Does 4,000, almost 5,000 gallons a minute at almost 3,400 feet of head and requires 20,000 horsepower to operate. When we talk about pumps, you have two major classifications, rotodynamic and positive displacement. Rotodynamic means that you have, it is a pump that combines both flows and pressures, where a positive displacement pushes full pressure, usually with some kind of mechanism that does not allow the fluid to move backwards, only forwards. Where a regenerative turbine falls into place is somewhere between a centrifugal pump and a positive displacement pump, like your piston pumps or plunger pumps, where you can get a really high amount of pressure, but you would maintain pretty low to moderate flows. So what is a regenerative turbine pump? Regenerative turbine pump is a rotodynamic pump that combines the high discharge pressure of a positive displacement pump with the flexibility of a centrifugal pump. So we'll look at some of the regenerative turbine pumps that MTH offers and how to select them here. Some of the other characteristics with the regenerative turbine pumps, besides the high pressure, are that they're usually a fairly compact design, uh, and that's because they have a simple construction. Usually, a single stage pump only has three major components in the driver, so it'd be a casing, motor bracket, and impeller. Um, they are pulsation free. When you have a piston pump or a diaphragm pump, you would have pulsation with that. Um, you wouldn't get that from a regenerative turbine. And the way ours operate, water is worked on both sides of the impeller at the same time. So the impeller is free floating on the shaft and will self balance as it's operating. And uh, regenerative turbine pumps have very good NPSH characteristics. That's not positive suction head. Um, Oftentimes, with a regenerative or with a centrifugal pump, you would have fluid being entered into the eye, and then it would be flung out from the outside or out to the outside. We'll look at that here. So when you have your fluid and it is going to the outside or getting introduced to the center of the impeller, it gets flung out one time, goes out the volute, and then exits the pump. So it only gets touched one time. With regenerative turbine pumps, well, if you want more pressure with a centrifugal pump, you would add multiple stages in front of that um, impeller so that each one could build up a little more pressure as it did its work um, throughout the entire process. With a regenerative turbine pump, instead of having multiple impellers to build up pressure, you have multiple vanes where the fluid gets worked over and over again. Um, and it just goes from one impeller vane to the other. By the time each time it goes through, it does the regeneration. That's where it gets its name. And then by the time it gets to the end, it hits this water stop and goes out the exit at a much higher pressure than when it started. And it does that on both sides at the same time. So when the water is introduced from the top, it splits and gets worked on both sides at the same time until it exits out. So comparing a multi-stage centrifugal pump with a regenerative turbine pump, um, here we have an example of a multi-stage centrifugal pump. This particular pump goes up to 25 stages, can do anywhere from a couple gallons a minute all the way up to, looks like they have run out set at about 24 GPM with a single P51 a pump with the impeller. Depending on where you need to be at the curve, we have a number of pumps, a number of models that could fit within the range of this pump. So we can, in some cases, even be able to replace this 23. If you need higher pressure yet, we could even replace a 25 stage pump with just a single impeller. Another comparison would be if you're familiar with Procon or Fluidotech. They use a rotary vane impeller, and that's a sliding vane. It slides back and forth as the shaft rotates, and it kind of scrapes the water or scrapes the side and then pushes the water out. That causes pulsation and also has moving parts that are touching. Part of the beauty of the regenerative turbine pump is that when you have the balanced impeller, there's no moving parts that are touching each other except for the mechanical seal. So talking about selection here. A few details that we would need in order to select a pump. The bare minimum details would be pressure, flow, temperature, and then it would have to be clean water because of those tight tolerances. It needs to be clean. Anything else other than water, we do have 2 application engineers that work full-time here that can help you select a pump. For reference, 1 PSI is equal to 2.31 feet a head. We publish all our curves using head and feet, and then we also have the head and meters right next to the head and feet, so you can see the comparison if you're using the metric system. And then every once in a while, you'll get a request for a pump that needs a pressure that they list in bar. It's not too common, but it happens. And then we use gallons per minute or liters per minute. There may be some other conversions, but we have that our conversion chart available on our website. So, and then we have the temperature differences. So, looking at the models that MTH offers as standard products, we have starting with our smallest pump is our P31, which is very close to what the T31 can do, and they get larger and larger until we get to our M series can hit the 1,000 PSI mark. And then we have some higher flows with the 140s and 150s. And then we do also have a line of centrifugal pumps that complement the regenerative turbine pumps very well if you need both. The very first way that we could select a pump is if one of the largest markets that the regenerative turbine pump was used for way back when MTH started was for boiler feed. And so we've spent a lot of time over the years figuring out which one of our pumps would fit with what kind of conditions. And so we have this boiler feed selection table that if we figure out that, or if we find out that we need a boiler that is a 30 horsepower boiler and the system pressure inside the closed loop where all the steam is being produced is at 50 PSI, we just take the PSI and the boiler horsepower to determine that we need a T31F third horsepower. Pretty straightforward, one of the easiest ways to select a pump. We have the same type of chart for flex coupled models or base mounted. Same thing, here we have a 25 horsepower boiler at 15 PSI for pressure is 141 with requiring a third horsepower motor. And we can go all the way up to 700 boiler horsepower, up to 250 PSI. And I think we even have a few that go higher past this chart. The next easiest way to select a pump, especially in the jockey maintenance fire pumps, is when you know what the main pump GPM rating is, as well as the system pressure. That's the pressure that all the piping is under inside of the system. Here we've got 1,000 GPM main pump, so we do 10% of that, which is 10 gallons a minute. Here we have 110 PSI is what the system pressure is, and so we have a P41L with a 1.5 horsepower motor. Moving on here, we have available on our website a cross-reference list, and here we have some specific models that we know we can replace with regenerative turbine pumps. One of them we have here is Aurora pump. We also have Burke's pump replacements, as well as Crane and Grundfos, and I believe the Payco and the Ingersoll dresser. At one time, we were actually private labeling for them, so some of these Payco pumps are our pumps. And then we can also do some Gould's replacement with some of our centrifugal pumps. Looking a little bit closer here, we've got the Burke's pumps. All of the Burke's CR, CT, and CS models are replaceable by an MTH model. In this case, we have a Burke's 7CT7M, and that would translate to a T41E on a 3/4 horsepower motor. With the 7CT is the 3/4. If it were a 3/7 CT, it would be a 3-phase. So this one is a single phase. So we have a comparison here of our curve versus the Burke's curve overlaid on top of it here. You can see that our curve can hit all the points needed that a Burke's curve would do, and it will do it even a little bit higher performance than the Burke's. And again, with our impeller doing all of the work of the fluid movement on the outside of the impeller, the NPSH can be much better on a regenerative turbine pump. So when you only have 4 feet of NPSH on a MTH pump, the performance would be reduced down to this line right here. On a Burke's pump, it's much lower. So you'd be doing between 6 and 7 gallons a minute with a MTH pump, but the same pump or the same hydraulics with a Burke's pump would only be able to handle about 4 gallons a minute. The next one that we have here is the Aurora pump. So we have a number of Aurora models. I believe these are all the 130 series models. And so we have, in this case, we have a 130 is the K5 is the impeller and water channel size, and we could replace that with a 151K, which would be very similar in hydraulics. And so we have the ability to replace several Aurora models because of that. Now we'll get into looking at some of the curves here. With a typical single stage composite curve, the first thing you need to do is determine what your overall GPM and feet ahead are that you're going to need. In this case, we're going to be looking at 5 gallons a minute with at 300 feet ahead, which we're going to use throughout this example here. So when we look at this, we have we'll go on the next screen on our website. All of the composite curves highlight. So when you look here at the 300 feet and you need your 5 gallons a minute, we can see that the D is going to be the ideal pump. So when you click on that, it opens up the individual curve for the D. And anytime you make any kind of a pump selection, if you were to imagine that this curve continued on all the way until it hit the 0, so you would have from 0 to a little more than 7.5 gallons a minute. At 50% of that, between 80% of the whole entire curve is the optimum operating range. That means that's where the best efficiency point is going to be for that pump, is between the 50 and 80%. So here we're looking at our 300 feet. We go across until it intersects the curve, and this pump, the T40 or T51D, will do a little more than 5.4 gallons per minute. And then to determine the horsepower, we look at the brake horsepower line and use that 300 feet to go down until it intersects the brake horsepower line. And we go over and we see that this this pump at this point needs a little bit less than 1 horsepower. So we would use a 1 horsepower motor in order to drive this pump. And then to see what the efficiency is, using that same 300, you go to where it intersects the main head capacity curve, and then you go up until it hits the efficiency point, and then over this pump, this particular pump is at 44% efficiency. When we talk about NPSH, NPSH is net positive suction head. You have net positive suction head available and net positive suction head required. The net positive suction head available is the amount of pressure that is at the suction side of the pump. The net positive suction head required is the amount of pressure needed for the pump to operate correctly. So when we look at NPSH at normal atmospheric pressure at sea level, the NPSH of water at ambient temperature is about 32 to 33 feet. So you already have 32 to 33 feet of pressure just in the atmosphere when you introduce a pump to it. So this is the NPSH of a cold tank. This is a 4-foot distance, and anything below 90 degrees is going to be above the 32 feet of head. That's going to be into the that's going to be at the atmospheric pressure, plus the 4 feet makes it 36 feet of NPSH available using a pump with a water level that's 4 feet above it. So when we start using the pump and we start having the system recycling back into the tank, and it starts getting warm at about 207 to 208 degrees, we're hitting the 3-foot marker on the NPSH. Here we're at that higher temperature, and when you have the 4 feet in the tank, you have a total of 7 feet of NPSH available. Some pumps have a hard time handling that. For the most part, a regenerative turbine pump would still be all right. So when we start looking at NPSH, the 300 feet, instead of performing at the full head capacity, we have marked the 7 feet of NPSH. So that would be if the water is at 207 or 208 degrees and it's starting to get close to boiling, the performance of the pump would actually decrease, but it would still work. So instead of doing the 5.4 gallons per minute, it's only doing about 5.2 gallons per minute. But it would still maintain the same horsepower and same efficiency. So then when we start getting to where the water is at boiling, the only NPSH in the water is going to be the NPSH of the water level above it. So in this case, we only have 4 feet of NPSH available if this water is sitting in this tank boiling. So once we get to the 4 foot, we use the 4 foot of NPSH marker, and we see that where it intersects at is only doing about 4.5 gallons a minute. So if you have boiling water, this pump will go from doing 5.5 gallons a minute down to 4.5 gallons a minute. So I just want to throw in here that we also have a version of our regenerative turbine pumps that are can motor pumps. For those of you unfamiliar with how the GAN motor pumps work, when the water is introduced, there is fluid that goes across the bearing, and then it goes through a thin liner in between the rotor and the stator, and then it goes back down across this bearing, which these two bearings, or all three of these bearings, are spiral drilled, so they promote flow. Once it goes in the back here, the shaft is hollow, so that it can travel through the shaft back to the front and then exit out with the pump. That whole process consumes about a half a gallon a minute. The difference being that there is no mechanical seal. Mechanical seal uses a thin barrier to be able to make a seal between the outside atmosphere and inside of the pump. Looking at the X41 series, when we're looking at our same 300 feet ahead at the 5 gallons a minute, we can see that the E is going to be the closest to the 60 hertz curve that can do that. It would actually underperform just a little bit at about 4.5. So you would have to estimate that you would need to use a VFD at 65 hertz to get that full 5 gallons a minute. And then the amps here, you could estimate that it would take about 6.2 amps to operate. So we'll start looking at the multi-stage regenerative turbine pumps. With the multi-stage regenerative turbine pumps, because there are 4 stages with a couple dozen models, we found the easiest way to represent those with a composite is to build it into a table. So we've pre-selected the pump that would be at the best efficiency at any given point. In this case, we have 75 feet with 8 gallons a minute would be an E41E using a half horsepower motor. With the 150, 160, and 170, these are the largest of our pumps. So you can see that here we have 150 feet ahead at 40 gallons a minute. And the proper selection for that would be starting at a 151L with a 5 horsepower motor. We'll get into some details now, looking at the 300 feet at the 5 gallons a minute. Here we have the 140E, 240E. The 140 would be just the regular regenerative turbine impellers by themselves. If you added the inducer, it would become a 240, and that would drop the NPSH. We'll look at that here in a minute. So again, just like the single stage regenerative turbine pumps, 50% of the curve to 80% of the curve is the optimal location for that. So here we're looking at 300 feet, and we want our 5 gallons a minute. So in this case, 2-stage will do that. So it's going to be a 142E. Figure out the horsepower needed for that. We have the horsepower curve listed below the regular head capacity curve, so you don't get the lines confused because they can be very close, and it would be a little bit harder to publish 4 stages all on one sheet, or all on one table or graph, so we do it in 2 graphs. So here we've got our 300 feet. It hits a little over our 5 gallons a minute, and we drop straight down until we hit the 2-stage horsepower line, and then we go across from there, and we can see that this pump hits just under the 1.5 horsepower mark. So we'd use a 1.5 horsepower motor to drive this with a 140 2E. When we start looking at the NPSH, when we get to the point where we have water that is close to boiling and the NPSH starts interfering with that, then you can add this inducer impeller, which is a Francis style centrifugal impeller in front of the suction side. It's built into the pump. And what that will do is that will allow the NPSH to drop, in some cases, down to less than a foot. So if you were dealing with 8 or 10 feet of NPSH required for the pump, and your liquid was so hot that you weren't getting that amount of NPSH available, you could use an inducer, and it would make it so the pump only required 1 foot. So in this case here, we have 300 feet with our 5 gallons a minute. The NPSH here is at a little bit above 3 feet. But if your tank is at boiling or the water level is lower, you use the inducer, it would drop that NPSH down to 1 foot. So, and you do have to add a 1/2 horsepower for adding that inducer. So when we look at the horsepower line, that same 300 feet, here we're looking at a little bit less than, this is a different curve, looking at a 2-stage. And as we go down, where it would fit the 2-stage curve, we're at about 1.4, but we need to add a 1/2 horsepower to be able to drive the 240 stage. So we actually go above the 1.5 marker. So you would need to upgrade the motor to a 2 horsepower motor instead of the 1 horsepower or 1.5 horsepower. Looking at the multi-stage M series pumps, these are the ones that can hit the 1,000 psi and still operate at quite a range here. In this case, I believe we are looking at 1,000 feet ahead, and here we're looking at 7.5 gallons a minute. So it's the same situation. You go across to the 1,000 until you intersect the amount of DPM that you need. In this case, it's a 3-stage. And you go down and you see that it does 7.5 gallons a minute. To do the horsepower, it's the same type as the flex coupled pumps. So you go down, you have your 3 stages, and you go down to the 3-stage marker and go across. This pump would require a 5 horsepower motor in order to operate. And then we have if you get into a situation where the pump is going to be close to shut off, you should never run a pump at shut off. But if you have it where the amount of pressure is going to vary in the system, you might want to consider using a relief valve. And the way this works is you set the relief valve at a certain pressure that you want to operate. Say you wanted to operate your system at 100 psi. That means that after 100 psi, it would start diverting fluid back to the source tank. And then the different sizes of the relief valves determine how much water can be moved back to the tank. So if you have your system set at 1,000 or at 100 psi, and you put a 1-inch relief valve, that means that it can move up to 34 gallons a minute back into the source tank. And then, as I mentioned earlier, we do have our C-series centrifugal pumps. They range all the way at about a maximum pressure of about 150 feet of head, but they can go out past 100 gallons a minute depending on which model you're after. So in this case, we're looking at a C41 CD on a 1/2 horse. When I say on a half horse, we designed all of these centrifugal pumps to be able to work with the service factor of the motors that they're mounted to. So when you buy a C-Series pump, it always comes mounted to the motor, and the motor has a service factor that allows it to operate above the rated brake horsepower of the motor. So in this case, we have half horsepower. When you look at the half horsepower on here, if you just use a 1.0 service factor, you would only be able to do about 50 feet ahead at about 23 gallons a minute. But when you go past the service factor, if you had a half horsepower brake horsepower with a 1.0 service factor, the 0.5 is the only brake horsepower you could use. But if you had a half horsepower motor that had, say, a 1.6 service factor, then you can use up to 0.8 brake horsepower. So in that case, you can run this pump almost all the way to run out without doing any damage to the pump or overamping the motor. And that is pretty much everything that I had to share. I've been watching the chat here. I don't see anybody with any questions. I want to thank everybody for taking the time to out of their day to sit through this with me and go over some of this. If you have any other questions, please feel free to contact me after this. And I'll have another webinar this afternoon on the website tour. So thank you very much and enjoy the rest of your day.